predicting the arrangement of electron groups around the central atom of a molecule. So we should define what an electron group is. Okay, an electron group is either a bond, and that can be single, double, or triple. It doesn't matter how many electrons are in it. It's going to take up roughly the same amount of space. So we count any kind of bond as one electron group, or it can be a lone pair of electrons, okay? Or lone pair, okay? So it's basically how many things you have to fit around the central atom. So what do you have to do before you do any of these kind of questions? You have to draw the Lewis structure first. And that is true for anything to do with VSEPR theory, which stands for valence shell electron pair repulsion theory, which is basically how you get from a Lewis structure to an actual molecular shape, okay? The molecular shapes come from a set of parent shapes depending on your electron group geometry. So the number of electron groups is also sometimes called the steric number, and steric refers to like space, okay? And again, it's literally the number of things you have to put around the central atom. So it's a sum of the number of bonded atoms plus the number of lone pairs. Bonded atoms plus lone pairs on central. Okay, so if we have two electron groups around the central atom, it's got to be bonded to two things. That shape is called linear, okay? If we have three electron groups bonded around the central atom, that shape is called trigonal planar. If we have four, that shape is called tetrahedral. If we have five, that is trigonal bipyramidal. And if we have six, that is octahedral. Okay, so I'm going to just quickly show you what those shapes look like. Okay, so this linear shape looks exactly like what you think it looks like, and that bond angle would be 180 degrees. So this is an example of how you get from that Lewis structure on paper to a more three-dimensional looking electron group geometry. Okay, so if our electron group geometry is three, you've got three things attached to your central atom, like this BH3 molecule here. That trigonal planar shape is essentially if you have 360 degrees and you divide it into three equal slices of pie, so that bond angle is 120 degrees. Now we're going to scooch on through. A tetrahedral shape would look a little something like this, okay? So although when you draw the Lewis structure, it looks like those angles are 90 degrees, if those are in 3 dimensions, that bond angle is actually 109.5 degrees. Now, a really good way to think of that tetrahedral structure is actually to put it inside a cube. What I mean is something a little bit like this, okay? It's not the prettiest of picture, but you can tilt the tetrahedral molecule shape, and you can see that if one of the atoms is at the front corner of the top side of a cube, then the other one will be at the back corner of the top side of the cube on the opposite side. And then on the bottom of the cube, your other two atoms will be on the opposite two corners, okay? So that's a really great way to help you remember what a tetrahedron actually looks like if you're trying to draw it in 3 dimensions. All right, so back to electron group geometry. So if you've got 5 things to fit around your central atom, then you are going to be looking at something a bit more like this would be a better representation. So as you can see, you have like a trigonal planar shape around the middle, or we call that the equatorial side, like the equator of the Earth. And then we have like a linear shape with the top and bottom. We sometimes call those the apical or the axial sides. So you've got 90-degree bond angles between the apical and the equatorial plane, okay? And then you've got 120 around the middle. So that's your trigonal bipyramidal. And then lastly, octahedral, you have that square planar type shape, but then with 2 axial atoms as well. So each of these bond angles is 90, and it's kind of like a jack shape, if you've ever seen those old toys, that whichever way up that is, it's going to be symmetrical. Okay, so that's what your octahedral shape looks like. So I guess we should probably get back to the question at this point. So how many electron groups are around the central beryllium atom? Well, we've got to draw this thing first, right? So beryllium then. Beryllium is in group 2, so it's got 2 valence electrons, and we've got 2 hydrogens, so each hydrogen has got 1 valence electron, so we've only got 4 valence electrons to play with. So this is going to be an example of one of those molecules that the central atom has an incomplete octet, and we're okay with that. So it's just going to be hydrogen, beryllium, hydrogen. Okay, so if we're going to count our electron groups, or a steric number if you prefer, how many atoms are bonded to the central atom? It's just going to be 2. There's no lone pair, so a steric number is 2. Therefore, my electron group geometry is linear. Okay, so I'm going to quickly run off a couple of examples of this so you can sort of see how quick you can get at this once you're in practice. Okay, the most difficult thing is drawing the Lewis structure first, of course. Okay, so we have the ClF5 molecule. So again, you have to draw the Lewis structure. So you have to top the number of valence electrons. So for my valence electrons, I've got 7 from the chlorine, and then I've got 5 times 7 from the fluorine. So I'm going to have a total of 42 valence electrons, okay? And when you draw the molecule, you will see that obviously we're already going to be hypervalent because, you know, we've got to put all these, come here, you, fluorine, do your thing. Okay, I'm going to just put this out very quickly. So we've got 2, 4, 6, 8, 10 electrons in bonds for the fluorine-chlorine bonds. And then we've got our lone pair electrons on each chlorine. So yeah, you do have to draw them. 10, 12, 14, 16, 18, 20. Sorry, it's going to look kind of ugly. 22, 24, 26, 28, 30, 32. I can't even draw this anymore. My mouse isn't working. 34, 36, 38, 40. Why is it not working? Anyway, you get the idea. I've only got up to 40 valence electrons apparently, so I'm going to have to put a lone pair on this central chlorine atom. So this is why it's important to draw the Lewis structure first, because if I just looked at that formula and said, ooh, chlorine pentafluoride, that must be trigonal bipyramidal. Okay, because if you look, I've got a lone pair on the chlorine here. Yes, that is a lone pair. Sorry, it looks ugly. So when we calculate our steric number, we have to acknowledge that that lone pair of electrons takes up space. So I've got 2, 4, I've got 5 bonds, okay, and I've got 1 lone pair, okay. So that means I've got a total number of things around my central atom of 6. So my electron group geometry is octahedral. Okay, so watch out for when you have lone pairs as well as bonded atoms on your central.